In this video, we'll continue with Biot-Savart law. Last time we looked at the magnetic field of a ring carrying current I, but at the center of the ring. This time we'll look at the magnetic field along the axis of the ring, a distance x away from the center. And so we've already done step one, namely draw the picture. And as we discussed in the last video, step two will be to consider what dl cross r hat looks like. So I'm going to begin by considering a small segment of arc length, in this case at the top of the ring. And in this case, dl points into the page. And so I can rewrite vector dl as scalar dl times negative k hat, again using our coordinate system, I, j, k. So out of the page would be the positive k direction. And then r hat, as we'll notice, has multiple components because it points towards our point of interest where we want to know the field. And so we can see that it has both I hat and j hat components. So in order to break r hat down, I'm going to introduce an angle theta, which will be the angle right here, pointing along r. And then we'll notice that that angle also appears right there. Maybe the image isn't best there, right? But if we zoom in, right, we can now break down r hat into its constituent components using that angle. And so with that, remember that r hat has magnitude 1, and therefore we can break r hat down into cosine theta I hat minus sine theta j hat, because our j hat component is pointing down. And so there we have it. That is dl across r hat. Now, importantly, let's pay attention. We can see that we have multiple components here. Unlike our previous problem, if we switch our position on the ring, our direction of dl across r hat is going to change. And so as we did with electric fields in earlier videos, we're going to utilize the symmetry of the problem. So I'm going to consider the dl, which is at the bottom. And if we look at the bottom, we can see that over here, we point out of the page, so we'll have dl k hat. And then what we're doing is we're taking the cross product. Our x component of r hat is the same as before. We'll have cosine theta I hat, but our y component is now pointing up, so we'll have sine theta j hat. Now, before we go ahead and fully compute those cross products, we can actually see what will happen without doing the full computation. If we pay attention, we notice a sign inversion between our dl's. We have negative dl k hat and dl k hat. And there's a corresponding sign inversion in our j hat component as well. What that means is at the top and the bottom, we'll end up having dl sine theta k hat cross j, but we'll get a cancellation where we have negative dl k hat cross cosine theta I hat versus dl k hat cross cos theta I hat. Those will produce opposite components, which will cancel out. Now let's fully do that out in case that doesn't make any sense. So I'll quickly run through the direct computation. So if we look at the top and we follow our circles, so we have ijk. What we have right now is k cross I. K cross I gives us j, but we've got our extra negative there. So we end up with negative dl cos theta j hat. And then for our second term, we have k hat cross j, which goes opposite our arrow. That gives us a negative sign. And then we have two additional negatives. So overall, we end up with minus dl sine theta I hat. Then if we look at the bottom, k cross I, as we said, is j, no additional negatives. So we get dl cos theta j. And if we then look at dl k cross sine theta j, k cross j goes opposite our arrows. And so we end up with negative dl sine theta I hat. So what does this actually mean? If we look at our point P, we can see that the top of the ring produces a contribution which has a component in the negative j direction and the negative I direction. So our magnetic field points this way. So this would be dB top, the contribution from the top. And then if we look at the contribution from the bottom, it produces a field with a positive j component and a negative I component, dB bottom. And so what that means is that we can now ignore our j component. In other words, with all the work that we've just done, we can see the j components cancel, and we'll simplify dl cross r hat. For the purposes of integration, we are just going to consider dl sine theta, or negative dl sine theta, I hat. Now, if that felt like a lot, we're now essentially almost done with the problem. And so let's move on to step 3, which is, of course, we're going to write out our integral, and we're going to ask if anything varies with our variable of integration. So Biot-Savart, we've got integral mu naught I over 4 pi r squared. dl cross r hat now just gives us sine theta dl. The negative I hat gives us direction, so I'm dropping that. Sine theta dl. That is our integral. And now let's ask whether anything varies with our variable of integration. As we go along the ring, does our distance from the point of interest for our magnetic field vary? I'm going to argue not. I'll argue that, in fact, r squared is equal to capital R squared plus x squared. And then again, looking at the geometry of our ring, we've got a right triangle with theta. So I'm going to argue that sine theta is opposite over hypotenuse. So sine theta is equal to r over square root x squared plus r squared. Which means that, in fact, we can skip step 4, which is setting up a coordinate system. No need for that, because we'll be able to pull everything out of our integral. And so moving on to step 5, we've got mu naught I over 4 pi r squared plus x squared times r over square root x squared. Let's just be consistent there. R squared plus x squared. And then all of that times integral dl. But of course, dl is being integrated along our ring, which means integral dl just becomes 2 pi r. So times 2 pi r. And with that, we can obviously do some simplification. And we end up with mu naught I r squared over 2 r squared plus x squared to the 3/2. And lastly, of course, we can bring our direction back and remember that this is going in the negative I hat direction.